Hello everybody, welcome back to the Gregorius Maths video. As you can see, I'm back home, back in London, back in business. And yeah, today is the start of well, this idea is taken from Flammable Maths. Because when I was younger, I used to really enjoy his maths advent calendars. And so, in anticipation of the birth of Christ, I too shall now be making one video a day until Christmas. And the reason, you might be asking, why didn't you start on December 1st? The reason for that is because I only thought of doing this after December 1st. So yeah, there you go, that's why. So hopefully I'll stick to it this year, and then hopefully next year you'll get the full advent calendar, 24 videos in a row. But okay, let's just focus on this year. Yes, so it'll be a mix of stuff that's more elementary and stuff that's a bit deeper, depending on what I've done that day. And then also, like Flammable Maths, I have something a bit more special planned for the final day, i.e. the 24th of December. So how are we going to kick off this advent calendar? Well, we're kicking it off with a nice result that was originally proved by Gauss, and we're going to give two proofs, which are both quite simple. So the result involves the Euler totient function, the Euler totient function. So I might as well define it first before we get into it. So phi of n is defined for some integer n, or so natural number n, and it's defined as the set of all natural numbers m, with m less than or equal to n, such that m and n are co-prime. Sorry, it's equal to the cardinality of this set. So for example, phi of 10, which numbers are co-prime to 10, which are less than 10? Well, we have 1 is co-prime to 10, 3 is co-prime to 10, 7 is co-prime to 10, and 9 is co-prime to 10. So that's 4 numbers I've just counted there. So phi of 10 is 4. Now, the result that I want to show is the following, and that is that if I sum over all of the divisors of some integer, of some natural number n, the Euler totient functions of all of the divisors, I just get back n. So as an example, let's consider 10. The divisors of 10 are 1, 2, 5, and 10. So if we do phi of 1 plus phi of 2 plus phi of 5 plus phi of 10, I claim by this that we'll get 10. So what's phi of 1? That's obviously just 1. Phi of 2, 1. Phi of 5, well, 5 is prime. So every natural number less than 5 will be co-prime to it, so we get 4. And then phi of 10 we just said is 4. So 1 plus 1 plus 4 plus 4 is 10. So, okay, that's an example of the theorem working. Now, let's prove it in general. And so I give two proofs in this video. And they're both pretty elementary, which is, I don't know, maybe somewhat surprising, because this result, when you look at it, there doesn't seem to be an immediate like way of, or at least to me, it doesn't seem immediately obvious that this should be true, or even immediately obvious how to go about proving this. But yeah, it turns out that it's actually not too bad. So proof 1, we'll do it in this little corner here. Proof 1 comes by considering the following. Consider the fractions 1 over n, 2 over n, up until n over n. There are two different ways that we can count the number of fractions here. The first is to say it's 1, 2, 3, 4, 5 up until n. That's just n fractions. So on the one hand, there are n fractions here. But there's another way of counting the fractions. If we simplify all of these into lowest common terms, how many fractions will there be with a denominator of n? Well, the answer to that is just 5n. by definition. I mean, if you're co-prime to n, then you're not going to be able to be simplified. And if you are, then you can be simplified. So the ones that are not simplified are the ones that are co-prime, and the number of that is given by the Euler totient function. Then, obviously, if we simplify, on the denominator, we're going to get a divisor of n. So the question is, for each divisor of n, how many fractions do we get? And here we can use the exact same reasoning to say, well, okay, if I have d on the denominator, then either I'm already in simplest terms, in which case the guy on top is co-prime to d, or I'm not in simplest terms, in which case the guy on top is not co-prime to d. And so the number of fractions which will have d on the denominator are precisely the ones which have the number on top, the numerator, being co-prime to d. So how many of those are there? Well, again, it's just, by definition, phi of d. And so the total number of these fractions is, we just keep doing this for every single divisor, and we get all the different fractions. So phi, because all of the fractions must have a denominator of some divisor of n. So phi of d1 plus up until phi of 1. And this is equal to n because there are n different fractions here. And so the sum over all of the divisors of n of phi of d is indeed equal to n. Like so. So it's just two different ways of counting how many fractions there are, and of course, no matter how you count it, they'll be the same number, so they must be equal to each other. And there you go. So that's quite a neat proof. You know, it's just a nice little trick, something interesting to spot. And there's a slightly more group theoretic interpretation of what's going on as well, which is maybe not so surprising. And here goes. So the group theoretic version, proof 2, let's say, is consider the cyclic group Cn, right? Now, every single element of Cn, the cyclic group of order n, will generate some subgroup, or some cyclic subgroup of Cn. And by Lagrange's theorem, these cyclic subgroups, well, the order of these subgroups must divide the order of Cn, which is just n. And we also know that, well, we maybe don't know, but I'm taking it as a given here, that any subgroup of a cyclic group is also cyclic. So what am I saying? I'm saying that the subgroups that each element of this generates are of the form CD, where D divides n. Okay. So now, what do we need to look at? Well, we need to look at how many elements of Cn generate CD, right? So let's say the generator of Cn is G. So what I'm asking is, if we pick some element of Cn, it's going to look like G to the k. When is G to the k, this subgroup generated by G to the k, equal to CD, right? So for which k, or like how many different k can we pick such that this is true? And, well, what do we have? Well, we need that G to the k has order D, basically. And for G to the k to have order D, well, let's think about this. We need k, what do we need? Well, we need k to not have any factors that are co-prime with D. Why is that? Well, because if k had any factors in common with D, then we would be able to, then k would have, G to the k would have an order of less than D. For example, if k and D had the same factor of 2 in them, then we wouldn't have to multiply d times. We wouldn't have to multiply d times to get a multiple of d. We can multiply d over 2 times, and because they're both divisible by 2, we would again get something which is a multiple of d, if that makes sense. Yeah, okay, so say k and d can both be written as 2n and 2m. Then if we had 2m times by d over 2, then we would get dm, which, again, if we're in CD, would have would be e, if what I've said makes sense. Basically, what I'm saying is, in the cyclic group CD, g to the k has order k over the greatest common divisor of k and d. And so, what I'm really trying to say is, the number of elements of this form that generates CD is exactly the number of elements that that are co-prime to D, and also less than or equal to D. Basically, that's what I'm really trying to get at. And since we have n elements here, and they all generate cyclic subgroups, we have that when you add up all of these possibilities, you get n. And that's what I'm trying to say. So, in conclusion, again, because the number of such k is equal to 5d, and we're going through each divisor d of n, because again, for it to be a subgroup of Cn, it has to divide n by Lagrange. And so, what do we have in the end? In the end, if we take all of this together, we get the result that we were looking for. I don't know. I hope you were able to follow that explanation. I think I made a slight meal of it, but hopefully you get the gist. Maybe after watching that twice. But anyway, yeah, these are two not so difficult, or at least not so long, proofs of this pretty nice result. And so I thought this would be a nice way to kick off the Advent calendar, which, yeah, should hopefully be a mix of some group theoretical results, some random integral sum things, some random algebra, or whatever I'm thinking about that day, that'll get posted. And hopefully I can actually stick to uploading every day until the 24th, and then, yeah, stay tuned for the 24th, basically. And yeah, I'll see you tomorrow, hopefully. Good day.